Okay, so hi everyone, I'm Ciara Loftus, this is Bruce Richardson, we're both from Intel, as you might have guessed. And today we're here to discuss some prototyping work, which ourselves and a couple others from Intel have been working away at for the last while. The work itself has been kind of driven by some challenges and trends with cloud native, particularly in the area of switching container to container or application to application, or east-west as it's often referred to as. So as regards an agenda, we'll elaborate a bit more on that cloud native type problem statement. We'll discuss how we switch today east-west using current approaches to vSwitching. We will put forth our proposed scalable vSwitching solution and discuss its many benefits, including just raw performance as well as better utilization of resources and automatic scaling. We'll discuss some next steps and we'll hopefully have some time for Q&A at the end.
So in terms of the problem statement that we've been looking at, given that this is an SDN room, I expect most people are familiar in some degree with SDN and in the comms world with NFV, Network Function Virtualization, which is very much a move away from discrete appliances towards more virtualized infrastructure where you've got VMs deployed on COTS hardware rather than custom boxes. But looking beyond that, we then see further trends towards containerization in this sort of cloud native, as it's referred to, style of deployment, where you take your monolithic VM, which may be using, let's say, 4 cores, as in the diagram here, or possibly 8, 10 cores, whatever it happens to be, and try to subdivide that further into individual containers or microservices formed into service chains, or intercommunicating containers of some degree or other to give you additional granularity of deployment and scalability. Okay? However, if we look at this from a networking point of view, we see challenges in terms of the amount of network bandwidth required. If you look at your monolithic VM, as shown here, where you may have, let's say, a 25 gig connection coming into that, if you break that up into 4 services, 4 service containers, you now have a whole bunch of additional traffic running between them that you have to manage as well. So your 25 gig network may suddenly shoot up to needing 100 gig or more, okay, because of this east-west traffic, as we refer to it. So if you've got real network out there and you're trying to send this out, your network infrastructure is going to hugely have to go up. But if you co-locate these on a system, we need to then see about how we handle switching between them on a virtualized switch within that platform, and how to handle these east-west connections on a single platform efficiently and with high performance for networking and communications is really the high-level problem that we set out to look at.
Okay, so how do we switch east-west today? So current approaches to vSwitching typically use a centralized model whereby a dedicated number of cores are nailed up and essentially reserved for the sole purpose of virtual switching. So for example, in this diagram here, we've got 2 of those nailed up vSwitch cores servicing 4 network functions. And a typical flow through one of those vSwitch cores would be, say, we receive a packet from network function 0, we parse it, see that maybe it's got a VLAN tag of 200. We consult our lookup table, see that there's a rule there to send those types of packets to network function 1, so we proceed to execute that action. So those types of operations, parsing, classification, they're pretty heavy duty, and as such your vSwitch cores are typically going to be pretty busy. And then with this extra east-west traffic, they're even busier. And then another challenge that cloud native brings is that we've got this kind of dynamic environment with workloads spinning up and down quite frequently. And there's a challenge there where the underlying infrastructure, the vSwitch in this case, needs to be able to respond to that increase or decrease in demand pretty instantly. Otherwise you run the risk of dropping packets or providing a poor service to your network functions or your tenants. So there's kind of a conflict here between the static vSwitch configuration with these nailed up cores and the dynamic environment with these workloads spinning up and down. And that leaves the operator deploying the vSwitch with 2 options really. Either they try and scale up and down vSwitch resources as the work scales up and down on the platform, but that's, it's pretty heavy-handed, it requires manual intervention, nobody really wants that. So the alternative then is to over-provision and just nail up a ton of vSwitch cores at the beginning, and then that way, over the lifetime, workloads will spin up and down, you'll always deliver a good service, but you've got a pretty poor kind of utilization of your resources. It's not very efficient. So there really does exist a need for a better solution without this manual intervention or over-provisioning, because neither of those options are really cloud-native friendly.
So in order to get scalability in a solution, we're looking at how can we distribute our vSwitch and try and co-locate the vSwitching requirements alongside our workload. The idea being that, yeah, you may have some traffic coming in out of a platform, but if you've got communicating entities on that platform, each of them is going to require a certain amount of vSwitching logic to it. So can we move away from having 4 cores on the platform, or 3 cores, or 8 cores, or whatever it happens to be dedicated for your vSwitch, be it OVS, DPDK, or whatever it happens to be, and instead put a little bit of vSwitching alongside each container on each core, as shown on the diagram on the right there. So in that way, we can then scale easier. So if you have a workload that's using 8 cores and your traffic rate in your network goes up and you now need to spawn off an additional 4 or further 8 instances, you are able to scale up vSwitching logic alongside that by co-locating them. If we manage to achieve this, okay, there are some other benefits we can get in terms of lower level efficiencies for moving the packets from one container or one application to another. So if we look at how we do this right now, if we want to send a packet from container 1 on core 1 to container 2 on core 2, we actually have to take 2 hops with that one packet. You have to send the packet from core 1 to your vSwitching core, and then from your vSwitching core to core 2. Okay, so there's 2 movements of data and possibly 2 packet copies involved there. Obviously, this is just an inefficiency. Any cycles that you spend, any CPU cycles you spend in either copying the data or trying to read it from remote caches or any of that, it's all just pure overhead. It's not actually doing the real work you want to do on the packet. Whereas ideally, we'd much rather a situation like this, where we can actually send the packet straight from core 1 to core 2. The challenge here is, how do you do that while still maintaining some degree of security, container isolation, all that good stuff that we want to have? We have restricted resources like our lookup tables, or the interfaces themselves, interface rings for VirtIO or whatever your interface type happens to be. Those all need to be protected. So if you put those inside the container, then we're giving an untrusted application access to restricted resources, so that's a no-go. If we put them outside the container, then how do they get accessed on the core? How can we do that? So even though I come from a DPDK background, as some of you may know, and work in user space all the time, I think in this case, for containers especially, the answer has got to be in the kernel itself. Because the kernel on the container, in the container world, the kernel is actually the host kernel. Okay? It's shared across all these, all the various containers on the system, and it's also, therefore, since it's on the host, it's a trusted environment where we can put things like lookup tables and VirtIO ports or rings of whatever connection type we're using. So we could switch in on the core from user space to kernel space to actually do our packet lookups and packet transfers. And what we looked to do was a prototype of this setup to see just how it would perform compared to the centralized vSwitch model. We implemented this using 2 DPDK applications that need to talk to each other on 2 remote cores. So how we set this up? Well, as in most cases, whenever you need to set up your network interface, you need to register some packet buffers. If we want to do a direct core 1 to core 2 transfer, we need to make sure those buffers are accessible from core 1 in the kernel. So what we do, whenever the second receiver container starts up and starts configuring its interface and registers its buffers, we then duplicate those buffer mappings down into the kernel space. This means that any core, when running in kernel space, can write to those buffers to copy packets in, but they're still isolated from the container because the container's in user space and it still doesn't have access to them. Then, after that setup is done, we can start transferring packets pretty easily. We can have our transmitting container make some sort of a system call. In our initial prototype, we just used ioctl for ease of use. Make a system call which switches us on that core into kernel mode. And one particular benefit we have here is that the packet we are sending is already in all our local caches because we haven't actually switched core. We've just moved from user to kernel on that one core. So we've got a lot of benefits from cache locality from using such a scheme as this. Anyway, once we're in kernel space, Then we can look to do our lookups. We can have lookup tables in the kernel configured by some external entity, whatever that happens to be. And we can do those table lookups. In our prototypes, we were actually working off OVS code base, so we actually transferred into kernel space the DPCLS, the table lookup routines from OVS to have some real vSwitching logic in there. And then we can do a single copy from source core to destination core. We don't need to do 2 copies. Our initial prototypes actually did 2, but we managed to get it down to 1 using the memory mapping scheme described here. So in that case, we can copy straight into the destination buffer, which then has the advantage that it potentially allows container 2 to receive that packet without having to make a system call itself. Because system calls are not the cheapest thing in the world. But one thing we do know from DPDK and other high-performance packet processing environments is if you have expensive operations, you can have schemes to get around them using amortization. And that's exactly what we're looking to do here. If you have to make a system call to transfer 32 packets from core 1 to core 2, it's not actually so bad. Especially when you compare it to, let's say, using a vhost virtio combination, the cost of one system call every 32 packets in terms of cycles is not that significant.
Okay, so how does our solution perform? So for our benchmarks, we took a fixed resource pool of 12 cores and a fixed workload. And at a very high level, we try and run as many of these workloads on our 12 cores as we can. So looking at the workload in a little bit more detail, we've got 2 applications. Each are using 1 core to encrypt and forward packets between pairs of physical and virtual interfaces. And then the part that we're particularly interested in is that we switch packets east-west between our 2 virtual interfaces using one of 2 different vSwitch implementations. So the first implementation is a well-known DPDK-based centralized vSwitch, and that of course uses an extra core to perform that switching operation. And then the second is a prototype of the solution we just described, which does not require that extra core because we've got our switching functionality up in the worker cores. So we chose the crypto workload because it's cycle intensive, and that way when we move our vSwitching up on the same core as the workload, you can kind of see the penalty that you have to pay. You take cycles away from your workload, and with the crypto workload, the cycles you take away will be critical to application performance, say, as opposed to if you were to use something like DPDK's TestPMD or some simple I/O forwarding app, the cycles you take away wouldn't be as critical to performance, and you wouldn't take as big of a hit. So it's just kind of to make the benchmark a bit more transparent. But anyways, to generate our data then, we send in iMix packets at 40 gig line rate into both ends of the pipeline, and we measure what we receive back and compare for both implementations. Okay, so the left here is our centralized vSwitch configuration, and you can see we're using 8 cores to run 4 of the 2 core workloads, and the remaining 4 cores in orange here are our dedicated vSwitch cores. So to kind of rephrase that, we're running 4 workloads, and we've got 1 nailed up core per workload, and that uses our full 12 core budget. And then for the distributed vSwitch, you'll see to run 4 of the workloads, we only need to use 8 cores because, of course, we're not nailing up dedicated vSwitch cores. Our vSwitch is running on the same core as the worker. That, of course, comes at a price. We're taking precious cycles away from our workload. We're not doing as much work, and in this case, the hit is 10%. So we're down 10% in the distributed vSwitch case, but we've got a 33% saving in cores. We're using 8 cores versus 12, so the 10% hit doesn't seem as big when you kind of consider the core utilization. And then an interesting thing to do is to take those 4 idle cores and do something useful with them, like run 2 more workloads. And then in this case, then we can kind of compare at a system level, 12 cores versus 12, both solutions. And in this case, the distributed vSwitch outperforms the centralized vSwitch by 31% when you use the full resource budget. So the kind of key takeaway from these benchmarks would be that you do suffer a hit at your kind of workload level, and your workload won't be as performant. But when you take a step back and look at the bigger picture, at your full resource budget and kind of utilization and all of that, the distributed vSwitch does appear to be the more compelling option of the two.
So, having heard all that, just some initial next steps that we're looking at doing. So we've done an initial prototype to show that there is potential benefit here, and that we can gain from putting the vSwitching logic alongside the workload, and it actually gives us some interesting benefits in terms of it dynamically balances how you spend your cycles. If you need to do a lot of I/O, you spend more time inside kernel doing switching. If you don't, you've got more time in user space for your actual workload. Other things we're thinking about doing is, the packet copies for large packets, they still are showing up as, a bit of a hotspot. So we're looking to see if we can look at doing copy acceleration using the Intel Quick Data on the Intel Xeon systems. So some links about that there. And also some of the, memory mapping stuff or switching to kernel space and all seem kind of familiar. Well, it is kind of like what's being done in AFXDP. And so we're looking to see, can we use some of the AFXDP infrastructure and rings and methods of using pull to get in and out of kernel space and to user space, and put this distributed vSwitching under that AFXDP interface type. And we've already had some discussions with Magnus and Bjorn about doing that. So that's on our radar as well, to kind of standardize it. And that's it from us.
Any questions for Bruce and Kira?
I obviously didn't go on long enough.
So for the distributed flow table, do you need to have the full flow table for each individual distributed switch instance, or are you also doing some cleverness where the distributed switch for each container or each workload only has flow rules relevant to that workload?
Will I take that?
Go for it.
Yeah, okay. Well, we're basing this right now off OVS and OVS DPDK, which already has its lookup tables per port. So this essentially means then our port is now basically our container instance, our container interface. So inside the kernel, you'll have all the tables, but each individual core will only be looking up the tables that are needed for the traffic coming from that core itself. So in that regard, they'll be distributed, and you get nice caching benefits. Rather than all the flow tables trying to fit into your OVS cores, you now have just a flow table for each individual container being in the cache of that container, of the core that container is running on itself. So,
Thank you, Bruce and Karen.